Hey everyone, guys, this is your J Educator Megha. I teach you live on an Academy Plus platform. You please check out my lectures if you have not yet checked. This is going to be a GOC series where we are going to discuss about the carboanions. We have already done with the carbocations and their stability. Now let's focus over the carboanions and their stability. Guys, I'm also a CSI UGC NET qualified with All India rank 25. I'm teaching you on an academy from last 5 years. I do have 127,000 plus followers. Okay, so if you are unaware of my classes and my courses, then please don't miss a chance. You will get my profile link from the description and the notes. Whatever the sessions I will be taking on YouTube, you will be getting the notes on our Telegram channel link, okay, which is also given in the description. So without any further delay, let's begin with this particular session, that is GOC, carboanions and their stability. Guys, first of all, to understand, let's have a look at what are carboanions. Carboanions simply suggests that we will be having a carbon and this will be having a negative charge on it. Is it? So carbon with a negative charge. So what does this mean? Okay, what type of structure it would be, and why we are looking for the carboanions and their stability. So this is the point. This is a question that is in front of all of us. So now let's have a look, guys. So when I'm saying carbanion, why when we are talking about a carbanion, a carbanion something looks like this. So why the carbanion is having only 3 bonded pair of electron and this negative charge is over the carbon like this. What it is all about? Let's have a look over the hybridization. Guys, we all know the carbon is basically the helium and this is 2s2 2p2 as the electronic configuration. When I am talking about a carbanion, the configuration, there is a gain of electron and because of the gain of electron, the configuration becomes 2s2 2p3. Is it clear? So this is in its ground state when the carbanion is in its ground state. Okay, so when this carbon is in its ground state, when I have to draw its orbital diagram, it would look something like this, that is 2s2 2p3. Okay, can it go into the excited state? No. Will there be a possibility of the jump of electron? No, no such possibility, because we do have only 2s, we do have 2p, but we don't have any 2d orbital, so we can't do any other thing. This will remain in its ground state, and so because of the reason this will remain in its ground state, this will undergo hybridization. Okay, this 2s and 2p orbitals will undergo hybridization and resulting into the formation of water. Ultimately we can simply see that here we are having a 3 unpaired electrons. So because of the possibility that we have only 3 unpaired electrons, they will undergo the hybridization. They will be going the hybridization. Okay, that is, they will be undergoing the bond formation, that is with the hydrogen atom. Okay, so these are the 3 hydrogen atoms which will be bonded with the carbon, because here the carbon, which was already having the 4 valential electrons, they were 4 in number. Because of the gain of 1 electron, they became 5 in number. So the carbon was having a 5 electrons, and by sharing 3 more electrons with the hydrogen atom, now there is a total of 8 number of electrons. So this is carbanion. So when you will see the structure of carbanion, you will find that these are the shared pair of electron, 1 2 3 4 5 6, and this 2s electron is basically the non-bonded pair of electron. This is basically the non-bonded pair of electron. Okay, so when you will see about its hybridization, the hybridization of carbanion is usually said to be sp3 hybridized. Carbanions usually said to be the sp3 hybridized. Why they are usually said to be the sp3 hybridized? Because here we can say that they have a tetrahedral kind of geometry. 3 bonded pairs and 1 non-bonded pair of electron. We can't say that this is a lone pair. We can say that there are 3 bond pairs. There we have 3 bonded pairs, 3 bonded pairs and 1 non-bonded pair of electron. Non-bonded pair of electron, non-bonded pair of electron. Okay, so this is the structure of a carbanion. So here we can say that this is sp3 hybridized and having tetrahedral as a geometry. Its geometry is tetrahedral. So if you want to jot down all the points related to the carbanion, so carbanion is basically having a total of 8 electrons. This is a 8 electron species. This is your 8 electron species. Okay, this is not electron deficient. This is a 8 electron species, out of which 6 are bond pairs. 6 electrons are in bonding, out of which 6 electrons are involved in bonding, and 2 electrons are in non-bonding orbital. They have not participated in bonding, non-bonding orbitals. Okay, so this is not electron deficient. Yeah, this is electron sufficient species. This is having a carbanion which is C negative. Okay, so whenever we have to prepare a carbanion, okay, they can be easily prepared by doing a heterolytic cleavage. So when you will do the heterolytic cleavage, you will be getting the formation of a carbocation and the carbanion, okay, by the heterolytic cleavage. So what I mean to say is, I want to say that this is the heterolytic cleavage. So by the heterolytic cleavage, we can get the formation of the carbanions, that is the anions, and this is your carbanion. And carbanions are usually sp3 hybridized. sp3 hybridized. What type of shape they would be having? Yeah, they would be having a geometry will be the tetrahedral. Geometry, we can say that this is the tetrahedral. But when you will looking for its shape, in the shape we only count the bonded pair of electrons. But the shape is pyramidal. The shape is pyramidal because in the shape we will just be counting this part. This and this. So this is forming a pyramid. So this is pyramidal in shape. Okay, now guys, there is one more thing that we need to know. You know, a carbanion could be something like this, that is CH3 CH2 negative. This could be a carbanion. So if this is a carbanion, I will be saying that yes, this is sp3 and yeah, this is sp3 hybridized. But if we do have a carbanion which is CH2 double bond CH2 single bond CH2 negative. Okay, let me remove this one hydrogen from here. Yeah, this is it. Okay, now if we will look for this particular molecule, what we do understand? This is CH2 double bond CH single bond CH2 negative. So you know that here this negative charge is undergoing resonance, and resonance is a game changer, right? I discussed this thing in one of my session. Resonance is a game changer. So what does it does? This is a game changer. So basically whenever we do have a resonance, the bond order gets changed, the hybridization gets changed, the dipole moment changes, the bond length changes. Okay, so because of the resonance there are many factors that gets changed. So if this carbanion is in resonance, then the hybridization of this carbanion will get changed. Okay, so when you will draw its resonating structure, you will find that this will become CH2 negative, CH. Here we will be getting a double bond and this will become CH2 positive. So ultimately when you will see the geometry of this particular molecule, this you will find that this is CH2. So here you will find that this is having a trigonal planar geometry. This is a trigonal planar geometry, and because of this trigonal planar geometry, so whenever there is a resonance, so when carbanions are in resonance, when carbanion is in resonance, geometry changes to, or the shape changes to, the hybridization changes to sp2. Okay, so these are the few things that we need to know about the carbanion. That carbanion is a 8 electron species, out of which 6 are in bonding orbitals and the 2 are in non-bonding orbitals. Carbanions usually forms by the heterolytic cleavage. We have to do the heterolytic cleavage to form the carbanions. They are sp3 hybridized, their geometry is tetrahedral, shape is pyramidal, but usually when the carbanion undergo resonance, it becomes planar. Okay, its hybridization will be sp2. Now here I do have few questions for you, and I want everybody of you to participate and to let me know that what would be the hybridization of that particular carbanion. So when this is a question in front of you, you can simply see that this is a negative charge and there is a pi bond. So we can see that this is X double bond Y single bond Z, and as I told you, X double bond Y single bond Z, over the Z, if you do have a negative charge, if you do have a positive charge, if you do have a lone pair, if you do have a pi bond, if you do have a vacant orbital, if you do have a radical, if you have any of such kind of thing over the Z, then this is a system for resonance. Then there we will be having a resonance, right? So definitely, because this is forming XYZ system, and here over the Z we do have a negative charge. So what we can say that? We can say that here we will be having a resonance, okay? And because of this resonance, the hybridization will become, this will go here and this will go here. Ultimately, what will be the hybridization for this species? Okay, I put Z. What will be the hybridization? This will become sp2. This carbanion is sp2. Here, is there any resonance? No, there is no resonance. No resonance means its hybridization is sp3. Here, if you would see, this is a carbanion, you know, here this is a carbanion. Now this negative charge is in resonance with this pi bond. They both are in resonance. You can see that this is X double bond Y single bond Z. Over the Z we have a negative charge. So this will undergo delocalization. Because this will undergo delocalization, we will be having the resonating structure, and so therefore when we will try to draw its resonating structure, we will found that this, there we will be getting a double bond. This becomes a negative charge, this becomes a negative charge, and this bond will remain as it is. Again we can show that there is a resonance. This will go here, this will go on this particular side. We can draw its resonating structure, and because of the resonance, the hybridization gets changed. Now this is it, and now again this negative charge will go there, this will go there, and we can draw more of its resonating structures. Now can you count that how many number of resonating structures we can get for this particular molecule? When this will go there, we have to break it like this, then we will be getting this. Now again we can draw its resonating structure. This bond will go here and this bond will go here. Again we can draw its resonating structures. Okay, so this is also one of the question that could be asked in your JEE Mains paper, that how many number of resonating structures you will be getting for this particular molecule. So we had a negative charge over there, then this, and then this, and then this. Okay, so at every carbon we are getting a negative charge. Okay, then this negative charge will go here, and then this. Then again ultimately we are getting it back. We are getting this structure back, this, and this. Okay, so the structure number 1, structure number 2, structure number 3, structure number 4, and the structure number 5. 5 resonating structures. 6 will not be considered. Why 6 will not be considered? Because this is same as 1. Okay, so that's why 6 will not be considered. Okay, so there are 5 resonating structures. The question could ask you. Okay, so guys, here we found that because this negative charge is in resonance, so this is going to be the sp2 hybridized. Okay, this is not sp3, this is sp2. Okay, that's why we can say that this negative charge is of a planar. This is in plane. Okay, this negative charge, this negative, this is a planar ring, and so therefore this is also said to be an aromatic ring. Why we call this as an aromatic ring? Why we call this as an aromatic ring? Because we know that this is a closed cyclic ring, and here we do have a planarity. Why we do have a planarity? Because yes, all the carbons were sp2, but this carbanion is also sp2. Because of the resonance, the hybridization is sp2. So yeah, this carbon is also planar. Okay, the second condition for a molecule to be aromatic. The third condition is delocalization. Yes, if every atom is planar, they will undergo delocalization of pi electron easily. And yes, the fourth condition is the Huckel rule. So yeah, here we do have 6 pi electrons, so this is aromatic ring. Got it? Now here if you will see the negative charge, this is not sp2, this is sp3, because there is no resonance. Here if you will see the negative charge, this negative charge is also undergoing resonance. So because it is undergoing resonance, this carbon is also sp2. Okay, so this is how we can identify the hybridization of the carbanion. Carbanions are usually sp3, but when they are in resonance, resonance changes the hybridization to sp2. Okay, so this is the criteria that is very necessary for us to understand whether the carbanion is planar or not planar. Okay, specifically while solving the questions related to the aromaticity, you need to know that. Okay. Now, let us focus over this particular question, how we can prepare carbanions. Okay, so yeah, before talking about the stability of the carbanions, we have first learned what are carbanions, what is the geometry, what is their hybridization. Now, how we can prepare it. So basically, guys, if we have any of such molecules, okay, and we treat them with a base, so you know what a base do. Base is a very good proton acceptor. If you will look for the definition of Bronsted base, you will know that this is a proton acceptor. Base has a high tendency to accept a proton. So when a base will accept a proton, then what will happen? Let's say this is your base, this will try to abstract the proton. So here this is the acidic hydrogen. So this is your acidic hydrogen. So this is your acidic proton. Acidic proton, so this base will be taking its acidic proton. Ultimately, we do have a heterolytic bond cleavage, and because of this heterolytic bond cleavage, we will be getting CH2 negative C triple bond N plus BH. Okay, that is a base, form a bond with the hydrogen. This is what happened. So ultimately this is a acid base reaction. Here this is a base, here we do have the acidic proton. So when a base abstracts the proton, it will result into the formation of a conjugate base. So this results into the formation of a conjugate base. And here in this conjugate base, we are having a negative charge over the carbon. So this conjugate base also termed as the carbanion, because we do have a negative charge over the carbon. That's why we are calling it as a carbanion as well. Okay, and this is the conjugate acid, and this is the conjugate acid. Okay, and ultimately this is the way, this is the pattern how we can prepare the carbanions. Now similarly here, if you will see in this particular question, there if we take a base, this is the acidic proton, okay, over this carbon. Why this is the acidic proton? Because this is the electron withdrawing group and this is the alpha position, and the alpha hydrogens are going to be most acidic. Okay, this is the alpha position, this is also the alpha position. So this hydrogen is very acidic. Ultimately this base will abstract this particular hydrogen, results into the formation of a CH2 negative N double bond O, this, and this carbanion is also resonance stabilized. Okay, so we can say that this is a sp2 hybridized carbanion. And here also this negative is also undergoing resonance, so this is also sp2 hybridized carbanion. So this is the way how the base can be prepared. The third question, here also we know that if this is the aldehydic functional group, so for this particular functional group, this is the alpha position, so we can abstract, so any of the base you can take, whether it is NaOH, KOH, anything. So just take a base, try to do the heterolytic cleavage, it will abstract the acidic hydrogen from the carbon, results into the formation of a carbanion like this, which is again a resonance stabilized carbanion. This is also sp2 hybridized resonance stabilized carbanion. Okay, so these are the stable carbanions because they are resonance stabilized, so resonance is stabilizing these carbanions. Now here we do have this also the alpha position, this is also the alpha position. So always remember, the alpha with less number of hydrogen atoms is always more acidic. So alpha with the less number of hydrogen atom is more acidic. Okay, so when we have a alpha carbon with a less number of hydrogen atom, that is this carbon is going to be more acidic. So when I will be taking any kind of base, this will abstract this particular hydrogen and resulting into the formation of CH3 C double bond O, CH negative and CH3. and this is also resonance stabilized. I hope you got the point. Okay. So this is also our carbanion, which is resonance stabilized. So this is the way how we can get the stable carbanions. And again, here this is also one of the example. This is also the acidic proton. This is very acidic proton, okay, because here we are having double conjugation. So this base will abstract this acidic hydrogen, resulting into the formation of carbanion. So this is how we can get carbanions. Okay, this is it. So ultimately we can say that if there is a carbon and here the carbon is having any of the hydrogen atom, and along with this carbon if there is any kind of electron withdrawing group directly attached to it, so what will happen, this hydrogen will become acidic. This hydrogen will become acidic. We can say that, we can generalize that, okay, or this could be any kind of R, this could be any R, okay, this could be any R. If we do have a carbon, if we do have a carbon with at least one hydrogen atom, at least one hydrogen atom, this could be another R, okay. So if we do have a carbon with the any R or R dash, at least one acidic proton. If we do have one of the acidic proton and along with the electron withdrawing group, because what does this electron withdrawing group do? This electron withdrawing group makes this hydrogen more acidic, okay. Then only when we will be treating it with a base, then this results into the formation of BH, there will be a formation of a conjugate acid and you will be getting C negative, this would be R dash, this would be R, and this would be any kind of electron withdrawing group, and this is going to be a carbanion. So basically we can generalize that this is a pattern how we can get the preparation of the carbanion, okay. So this is the general method, a generalized, I have generalized this mechanism that how the carbanion gets prepared, okay, how the carbanions gets prepared. Now the question is about the stability, how we can stabilize the carbanions. Guys, carbanions, usually the carbanions which are very aromatic in nature are usually more stable. Let me give you an example. I have already taken this as an example for you guys. This is a pi bond and this with a negative charge, okay. So this is going to be the aromatic carbanion, and if I take an example like this and this with a negative charge, this is an example of an anti-aromatic carbanion. Why? Because here the carbon with a negative charge means there is a carbanion, and this carbanion is a part of that closed cyclic ring, okay. So if you will see in both the examples, this is a closed cyclic ring. Yes, absolutely, this is a closed cyclic ring, and in this closed cyclic ring, you know that if this negative charge is in resonance, okay, if this negative charge is in resonance, this is undergoing resonance, then ultimately we can say that this is planar, then every atom is planar. These are sp2 already, they were sp2, and this negative is also sp2, means they all are planar. The planarity, the second rule has to be the planar. The third thing, there must be a delocalization. Yes, there is a delocalization of pi electron, can easily delocalize throughout the ring, and the number of pi electrons are basically 6 pi electrons, which is actually obeying the 4n plus 2 pi electron rule. And so because of this reason, we can say that this is an aromatic carbocation which is highly stable. And here what is happening, here this is a closed cyclic ring. The first point is clear. The second point, this is planar. Yes, absolutely, the negative is in resonance with the pi bond, so yes, this is also sp2. The third point, that there has to be a delocalization of pi electron. Yes, there will be a delocalization of pi electron. The fourth point, there are 4 pi electrons, and when we have the multiple of 4, that is when we have 4 and pi electron, this results into the anti-aromatic, and so therefore anti-aromatic carbanions are least stable, okay, just like in the case of the carbocations. Aromatic carbocations are more stable, and the anti-aromatic carbanions are least stable, okay. So this is the point that we have to focus. Now after that, okay, we do have the carbanions where we do have a resonance, okay. So if you will be having two examples, Let's say here I am having a example of a carbanion. This is my carbanion, and here this carbanion is in resonance with this pi bond, and here I do have a carbanion, and here this carbanion is not in resonance. Okay, so these are the two examples. So which factor is applying there? Here we can't say that this is aromatic because this is a cyclic closed ring, but this is not a cyclic closed ring. So there is no possibility of aromatic. This could be only resonance. So here we do have a resonance. Okay, so this negative charge is undergoing resonance, and resonance is stabilizing it. But here if you will see at the alpha position, we don't have any other thing, but we do have the alpha hydrogens. We do have the alpha hydrogens. So only the alpha hydrogens will be a part of the hyperconjugation, and they will be stabilizing the carbanion. Okay, this is it. Now we could have an example of inductive effect. So basically what happens in the case of the inductive effect? Let's say we do have a carbanion. Here we do have a carbon chain, carbon chain, carbon chain, and here we are having the NO2 group attached. Okay, this is the NO2 group. Let me draw the structure neatly. I can also show it like N double bond O, and this would be the O. Okay, something like this. This is the structure of NO2 group, so I drawn it like this. So this is the NO2 group we would be having. Okay, if you want to focus over the bond angle, let us do it bit more correct. How we can do? We can draw it like this. Okay, this is the NO2 group we have, or we could have any kind of thing, this, or here we could be having any kind of chlorine, bromine, or any other thing that you can say, any such group. Okay, any such group. Let's say I have put 3 methyls. Okay, so what has happened? What will you notice? So basically we will notice that over this particular carbanion, there is a group. Is there any resonance? No. Is there any aromaticity? No. Is there any hyperconjugation? Hyperconjugation, we could say that there are 2 alpha hydrogens, 2 alpha hydrogens, 2 alpha hydrogens, but they are the same in both the cases. But ultimately we can see that there is a NO2 group. NO2 group is showing inductive effect. What type of inductive effect? This group is causing minus I effect. This group is causing minus I effect. And if you will focus over this particular group, this group is causing, this is causing plus I effect. So who will stabilize this? Okay, guys, always remember, delocalization or dispersion of charge leads to stability. Leads to stability. Are you getting? Delocalization or dispersion of charge. Here you were having the delocalization of charge, there also the delocalization of charge. So delocalization or dispersion. Now there is no possibility of delocalization, but the dispersion could also be there. Dispersion means distribute the charge. How a charge can be distributed? If we do have a group with the minus I effector, if this group is having a tendency to pull the electrons towards itself, if this group is withdrawing in nature, so what this will do? This will try to distribute, or this will try to disperse this negative charge throughout the molecule. So the dispersion will occur. Okay, so here we do have a dispersion of electron. So here in this case we can see the dispersion of electron. Ultimately this will lead to the stability. Okay, and here in this case what you will notice, this is a plus I effect. This will try to give more of its electron. If this will try to give more of its electron, the charge will travel, and the intensity will increase. So are we doing the dispersion of electron? No, we are increasing the more number of electrons electrons over the carbon. So our carbon is getting highly charged. Okay, so this carbon is basically getting more charged. So ultimately we can't say that this is stability. Okay, here what we are doing, we are excessive of charge. There will be the excessive or accumulation of charge. Excessive or accumulation of charge will occur. Accumulation of charge. So whenever we do have accumulation of charge or the intensification of charge, or when the charge gets more and more increased, then this leads to instability. This leads to instability. Okay, so we can say that here if we do have the inductive effect, we have to focus over the inductive effect. Then always remember, the minus I effect will stabilize rather than the plus I effect. Okay, similarly, if you do have a resonating effect, we could have some of the cases like where we have a carbanion, and this carbanion is bonded with any kind of group which is like NO2. Okay, so now here what we are having here, this negative charge is in resonance with this NO2 group. Okay, and we could have a carbanion, and this carbanion is in a resonance with any other kind of group which could be showing any kind of plus R effect, we can say that. Okay, so any of the group which is minus R in nature, if it is minus R in nature, then only there is a delocalization of charge. This will leads to stability. Okay, so minus R increases the stability rather than plus R. Minus I increases the stability rather than plus I, because they will delocalize or disperse the electron. That's why, this is the reason. Now similarly, if there is a question of the hyperconjugation, we can say that the minus H will stabilizes rather than the plus H. Okay, so if you want to summarize it, we can say that the minus R, then the minus H, then the minus I, then we can say that the reference atom, hydrogen is the reference atom, we can consider. Okay, and then after the plus I, and then after the plus H, and then after the plus R. Okay, so that will be the groups that will decide the stability of the carbanions. Okay, if there is any such group, because we know that resonance is more predominating factor, then the hyperconjugation, then the inductive effect, That's why the groups which are minus in nature, why? Because whenever we do have a carbanion, and if we do have a groups which are minus, which will delocalize or disperse the electron density. So such groups which are minus in nature, which are deactivating or withdrawing in nature, will stabilize this carbanion. Okay, so that's why this is the order that we need to understand. I hope you understood why the aromatic are more stable. Then comes your resonance, then comes your hyperconjugation, then comes your inductive effect, okay, whether it is plus I or minus I, then comes the percentage of S character. So what does this mean? Guys, this is the last factor, and this simply says that you do have a carbon with a negative charge. You do have a carbon, this is your carbon with a negative charge, or you do have a carbon with a negative charge. If you will see all the three cases, okay, what you will understand, in all the three cases you will come to a conclusion that this carbanion is sp3 hybridized, this carbanion is sp2 hybridized, and this carbanion is sp hybridized. Okay, so as the percentage of S character increases, the electronegativity increases. Let me tell you. So what I am telling you, please focus. As the percentage of S character increases, the electronegativity increases. This is a sign of electronegativity. Okay, capital Psi. So as the percentage of S character increases, the electronegativity increases. As the electronegativity increases, as and when the carbon will become more electronegative in nature, the nature of the carbon becomes more electronegative, the stability of negative charge increases, the stability of carbanion increases, carbanion stability increases. Why? You know guys that you always put the charge as per the nature of the atom, right? If I give you the example like if I give you the example like, bache, I do have a sodium and I do have a chlorine. Okay, so over the sodium you will put a positive charge and over the chlorine you will put a negative charge. Why? Depending upon the nature of the atom. You know that sodium is electropositive, this is electropositive. So because it is electropositive in nature, it is metallic, you will put a positive charge, and this is an electronegative atom. So when any of the atom is electronegative, relatively electronegative, you will put a negative charge. So similarly, they all are carbons. They all are carbons. But this carbon is more electronegative. So since this is more electronegative, the negative charge will be more stable. Okay, so if you ask me about the stability order, the carbon, this particular carbon with the negative charge is less stable than the carbon with this particular negative charge, and the carbon with this as a negative charge. Why? Why? The reason is very clear. Again you can write it. This is the stability order because this carbon is sp hybridized. Sp means it has maximum percentage of s character. The percentage of s character is 50%, and here this is sp2 and here it is sp3. So as the s character increases, here we do have maximum, that is 50% s character. So as the s character increases, the electronegativity increases, the stability increases. So out of all these carbanions, this carbanion is most stable. Okay, okay, because depending upon the nature of the atom. So this carbon is having more electronegative character. So as per the negative character, the negative charge will becomes more stable. Okay, so if you have any doubt, you can let me know. Okay, and guys, there is one more thing that I would like to tell you. Ki whenever you draw any of the carbanion structure, okay, just like see here in the case of the example number 5. Here we do have a carbanion. If you will draw its resonating structure, you will find that we do have CH double bond C, and this will become O negative. This will be O, CH2, CH3, and this will remain as it is, CO, CH2, CH3. Okay, so these two are the resonating structures. So what is the difference between the two? If you will talk about the stability, so this is a carbanion, this is also a carbanion, this is sp2, this is also sp2 because of the resonance, but here the negative charge is, this is a less stable, this is less stable, and this is more stable. Why this is more stable? Why? But if you are talking about a carbanion, this carbanion is stable because of the resonance, but when you draw its resonating structure, the negative charge over O is more stable rather than the negative charge over the carbon. Why? Because charge is stable as per the nature of the atom. Okay, so this is more stable, this is less stable. But if you are talking about a carbanion who will be a good nucleophile, who will be more reactive, so reactivity will be opposite. Okay, if it is more stable, this is less reactive. This is less reactive, and if it is less stable, this is more reactive. This is more reactive. Okay, you might already know stability is inversely proportional to reactivity. If the stability increases, the reactivity decreases. So if it is more stable, it will be less reactive. Okay, so this is it. So just a go through a quick revision. I told you about what a carbanion is, how we can find out their hybridization, their geometry, how we can focus over. This is it. Resonance was a game changer. So that's how the carbanion could be sp3 or sp2. I have given you few examples to make you understand how to identify whether which is sp3 or sp2. Okay, then I told you how we can do the preparation of the carbanions. Carbanions can easily be prepared by taking any of the species along with the electron withdrawing group, because electron withdrawing group will give you the acidic hydrogen, and whenever we will be taking a base, so any time when you will be taking a base and this base will react with the acidic hydrogen, there will be a formation of BH and you will be getting the conjugate base, and this conjugate base can also be known as the carbanion. Okay, but this has to be a stable conjugate base. Now for the stability of the carbanions, I told you please learn that particular order. The aromatic are most stable, anti-aromatic are least stable, and in between them there is a resonance hyperconjugation inductive effect, that is RHI. RHI, resonance hyperconjugation inductive effect. Okay, then comes your percentage of S character. This is it. Okay, so again repeat, what will be the order? Again repeat what will be the order. Aromatic are going to be the most stable, aromatic are going to be the most stable, anti aromatic are going to be the least stable, anti aromatic. Okay, and what else comes, guys? Here we will not be having just like the carbocations, we could not having any kind of miscellaneous or substituted category. Okay, we do have the resonance, we could have the resonance because of the pi bond. Okay, there could be a delocalization, there is a possibility of delocalization or dispersion. Resonance, then comes your hyperconjugation, and then comes your inductive effect. Okay, that is RHI. Please learn RHI: resonance, hyperconjugation, inductive effect. And then after this resonance, hyperconjugation, inductive effect, there comes your percentage of S character. And how to understand the percentage of S character? I told you, the negative charge will be more stable over the more electronegative atom, and the positive charge will be more stable over the more electropositive atom. Okay, so depending upon the nature of the atom, they will carry a charge, and so therefore anti-aromatic are going to be the least stable. So this is it, guys. If this session helps you and you learn good about the carbanions, then please you do like this particular session and subscribe for our channel, and do follow me on Academy. You could be having a better chance to learn through the online platform. Many of the students are very confused, ma'am, whether I should go with online or offline. Guys, if your motto, your target is very clear that you want a J selection, then yes, you can save your time, you can save your energy, and you can save your efforts, and you can maximize them by learning through the online platform. Okay, because ultimately you have to work on yourself. Okay, so more the time you will give, more practice you will put, you will be able to make your clear your concepts. Okay, so why I'm teaching on YouTube for free? Definitely so that I could be a part to revolutionize the education. You people may get the quality education over from the free platform as well. There are many of the students, those who are learning from the remote areas, and they cannot afford the good lectures. They can't get the quality education. Okay, because of the excess of because of the limitation of resources or the limitation of good teachers. But yes, this online education has its own revolutionized way. Okay, so now everybody, anybody at any corner of the country with an access to the internet can get all such lectures from us. Okay, so I want you all to understand that how we do teach on an academy. Okay, this is the same way, the same pattern. We do have our own website which facilitates and makes the process much easier, so that all your doubts may get clear. You get complete lectures, you get DPPs, you get the complete handwritten notes from us as well. You do the practice tests, you can evaluate your rank. There is a rank predictor, you can predict your rank, that how you people are doing among all the students across the country. So there are many other things that an academy platform offers you. Okay, so this is just a taste for you guys. If you really enjoy learning from us, then you do let us know, and you can also join us on our Unacademy Plus courses which we are already taking. And for that you just need to follow me. Okay, just visit my profile, google it, Unacademy Meghamam. You will get my profile open. Just follow, just click over that follow button. Okay, and you will be able to see the feedbacks, that 6,000 plus feedbacks that we are having over my profile. There are 32 million watch minutes, and 1 million plus students have already learned through me and my courses. 1 million, 1,27,000 students have already have learned through me and my courses. So guys, why you are not been a part of that? There are many free courses and many free special classes that we have created over an academy. So it not just that you have to pay for at first only. Okay, you just go through the lectures, and if you feel ki, yeah, this is the right thing, this is the right platform, from here I could learn, then only you go a step ahead, get the subscription, and yes, start your preparation. Okay, why there would be a delay? Just buy one subscription, you will be getting the access for all the subjects. Okay, from the best faculties. Okay, so guys, you can also use my code, which is Meghamam. which is Meghamam, and learn through us. Okay, so there are so many things in the description. Please do have a look, and yeah, see you later. And if anything comes to your mind, please drop it in the chat section. I will definitely have a look on it. Bye bye guys, take care.